related to the talk of Howard Rosenberg about the existence of constant mean curvature surfaces in manifolds. But the only difference is that I do not consider a very special type of manifold, and I will only deal with a very general manifold, so a generic one. I will try to explain what it means. What I'm trying to do is to provide enough examples which can be found in basically any Riemannian manifold. So in most of the talk I will assume that I'm working in dimension 3. So M3 will be a compact Riemannian manifold. But many things I will say also hold in a higher dimension and even in dimension 2. But to make things simpler, I will focus on dimension 3. And so the problem is to understand constant mean curvature surfaces which are embedded in M. So in a higher dimension, everything will be, a lot of things will be true for hypersurfaces, constant mean curvature hypersurfaces, or also embedded in manifold. So to start with, what I will do is that I will give you two examples and remind you of a very classical constant mean curvature surface in maybe in a way slightly different from the way you have you know them, and then I will explain to you why this type of surfaces they extend in a very general framework. So maybe the easiest thing to do is to start with a torus, a flat torus. Okay, and the problem is, do you know any constant mean curvature surface in a flat torus? And the answer is yes. So the first type are spheres. And in fact, what you can do is that you can start with a point, and then you can have concentric spheres of radius going from 0 to some maximal radius, which is probably 1/2. And the mean curvature here is 2 over r. And so for me, the mean curvature is the sum of the principal curvatures, but not the average. So if this is the sphere of radius r, then the mean curvature is this. And you can see that if all the spheres are centered at a point, then this produces a local foliation of the torus by concentric spheres. Very important in my talk will be the Jacobi operator. So the Jacobi operator appeared already in many talks, and so the Jacobi operator about the sphere of radius r is just the Laplacian on the sphere, S2 plus 2, and here there is a factor 1 over r squared. And the key point is that, so the key point to remember is the fact that this operator here has a kernel. So Laplacian S2 plus 2 has kernel. And in fact, it is very easy to find out what is the kernel of this operator. These are just the coordinate functions which are restricted to the sphere. So there are 2 coordinate functions, 3, excuse me. And in dimension n, there will be n coordinates function. And but the thing you have to remember is that this Jacobi operator has a kernel. Okay. Next, the second extremely easy example, which still holds in the flat torus, are cylinders. Okay, so this time take a cylinder, a vertical cylinder. Let's say the radius is r, and well, now the mean curvature is 1 over r. And what is interesting is that as r tends to 0, you see that the sequence of cylinders concentrate and becomes, you lose one dimension and it becomes a straight line. So as r tends to 0, you have convergence to a straight line. Okay, now let's work out the Jacobi operator about the sphere, about the cylinder. So let me call the vertical variable, let me call it t, and let me call the angular variable theta. So the Jacobi operator about this cylinder here reads dt squared plus 1 over r squared d theta squared plus 1. Okay, so this time it is very interesting because again you see that this Jacobi operator has kernel. So now J has kernel, and again it's very simple. You see that the function cosine theta and sine theta, which are independent of t, belong to the kernel of your operator, and but these are just the coordinates function restricted to a circle. But also what you find out, so first of all, that this is 0. But next what you find is also that cosine 2 pi, who knows, kt is equal to 0 provided k is, the radius r is chosen to be 1 over 2 pi k. And k is an integer. Okay, so from time to time, so the idea is that from time to time, when r has a special value, you find out that your Jacobi operator has more kernel than it has usually. Now, let me point out that the kernel of this operator here and these two functions here are closely related to some geometric properties of the problem we are studying. And the idea is that the mean curvature is invariant under rigid motion. So the fact that you have here a three-dimensional kernel reflects the fact that if you have a sphere, you have three ways to translate it in space, and you don't change the mean curvature. And here, if you have a cylinder which sits inside this torus, what happens is that you can translate in the horizontal variables, and this is reflected in the fact that these two functions belong to the kernel. Now, the fact that here from time to time you also have an extra kernel is related to the existence of what are called Delaunay surfaces. And Delaunay surfaces are surfaces of revolution which have mean curvature, and they can be depicted as follows. So basically they are periodic surfaces in one direction, and they oscillate, and they have mean curvature. The mean curvature can vary, and can be 1 over r if you want, and they are surfaces of revolution. And the fact that here you have kernel, you have some kernel, can be interpreted in the sense that for some radii carefully chosen, you have a bifurcation phenomenon, and this bifurcation phenomena allows you to state that the straight cylinder bifurcates into something which still has constant mean curvature, but now is not a straight cylinder and oscillates like this. Okay, and so Delaunay surfaces are completely understood, and you can work out that you have many different if you work in the three torus, you have many different families, and all the families, they are smooth families, and they converge to some singular constant mean curvature surface. So first, for example, the first bifurcated branch converges to a sphere, which sits inside the three torus. The second branch of bifurcation converges to two spheres which are tangent to each other and align along the vertical axis. And the third bifurcation branch converges to three spheres which are supposed to be of equal radii, and so on and so forth. So what you have to keep in mind is that, unfortunately, what happens is that the Jacobi operator about a cylinder is not always invertible for two reasons. First of all, you have the action of rigid motion, and secondly, what you have is that you have this bifurcation analysis, which exists in this case. Now, if we were to work, so the last thing I want to mention are doubly periodic CMC surfaces. In fact, in the language given by Howard Rosenberg, this would be bigraphs. And they can be understood as follows. So you imagine that you are in the 3 torus, and what you do is that you take two copies of a 2 torus, flat 2 torus, horizontal torus. Okay, and the idea is that if the two copies are close enough, then what you can do is that you can perform a connected sum between the two copies. So here you can glue the two copies by a catenoid and perform a connected sum. Maybe like this. Yeah. Between the two copies, and what you do is that you obtain a constant mean curvature surface with mean curvature is epsilon close to 0, and which is exactly obtained by taking two flat tori and connected them by a small catenoid. Okay. Right, but this exists for when the mean curvature is close to 0, while this exists when the mean curvature tends to infinity also. So what is quite interesting is that all these three surfaces I've tried to describe are not specific to the flat 3 torus. And in fact, if you think about S3, you can find out exactly the same type of surfaces. So, for example, spheres in S3. So this is extremely simple. So now what you have is that here this is a picture of S3, and you can foliate S3 by parallel S2s, and the mean curvature of these. So the equator here has mean curvature 0, and the mean curvature goes from plus infinity to minus infinity here if you take a very small sphere here or very small sphere there. But again, what you have is in this case, a complete foliation by concentric spheres of the S3. Slightly more complicated, you have constant mean curvature tori in S3. And in fact, these are very simple to describe. So you take two radii, R1, R2, and you compute R1, R2 in such a way that this sits in S3. So you have R1 squared plus R2 squared is equal to 1. And then you compute that the mean curvature of this, which is constant, and is given by 1 over R1 over R2 minus R2 over R1. Again, what you can do is that you can compute the Jacobi operator about this torus, and you find out that you have a bifurcation phenomena exactly in the same way I described in the flat 3 torus. So again, there is a bifurcation phenomena as, let's say, R1 tends to 0. And so this gives rise to what are called Delaunay tori in the sphere. And they are exactly the way you would describe them. So instead of having a torus of revolution, what you have is that you have a torus that starts having some bubbling. Okay, and so the number of bubbles can be, unfortunately, you cannot have only one bubble in this case. It starts by 2, and then 3, 4, and 5, and so on. another feature which is very interesting is that as R1 tends to 0, then you see that if this radius tends to 0, you see that your sequence of concentric tori, what they do is that they condense over a great circle. So you see that the tori converge to some great circle. Now, let me try to describe what is going on with the bifurcation phenomena and the Delaunay tori in the sphere, because this will be quite important. So picture will be much harder to do, but so here you have to imagine that this is one of the torus that starts to bifurcate, and what will happen is that instead of having a torus of revolution, what you have is that this torus start to become a bit bumpy here and has a waist from time to time, and it has to be periodic along, let's say, this direction here, and as I said, the number of places where the torus becomes bumpy is at least 2. So what you have to picture is that now you have this kind of tori embedded in the sphere, and they start to become bumpy, and in fact this produce a smooth family of constant mean curvature tori. The mean curvature varies, and at the end of this family you end up with a situation where you have spheres S2 which are aligned along an equator. So this here, at the extreme end of the family, what you obtain are spheres, small spheres, which are arranged along an equator in S3. Okay, and so right just before this, you reach this critical situation, what you can have in mind is that the surfaces you obtain, they look like these spheres connected by small catenoidal necks. Right. As I said, the least number of spheres that arise in this way is 2. So in the case where you have 2 spheres, then the picture is slightly more complicated to understand because I cannot draw it in this way, but there is a very interesting way to understand it. So the bifurcation branch, when you have only 2 spheres at the end of the family, can be pictured as follows. So you take S3, and here you take the equator S2, and what you do is that you leave this as a constant mean curvature surface which is slightly above the equator and one which is slightly below the equator. Okay, and this distance is supposed to be very small, let's say epsilon. And then what you do is that you can connect these 2 spheres. So this one is a S2, this one is a S2. You can connect them by small catenoids on 2 antipodal points. So the first bifurcated branch, you can picture it as being a doubling of 2 S2s. So the equator here is a minimal surface, but what you do is that you double it, and then you perform a connected sum at 2 points, antipodal points. And this is called a doubling construction. And this is very reminiscent of what I've done here. So here I've tried to explain that in the flat 3 torus, what you could do is that start with 2 tori which are flat and perform a connected sum between them at one point and produce a new constant mean curvature surface. So when epsilon tends to 0, this family converges to 2 copies of the flat torus, and here as the height epsilon tends to 0, this converges to 2 copies of the equator S2. So this doubling construction has been used by Nikolaos Kapouleas and Seodong Yang to produce a new minimal surfaces in S3 by doubling the Clifford torus. So what they did is that they perform exactly the same type of construction. But starting from the Clifford torus, which is one of the tori here when the two radii are the same, R1 is equal to R2 equal 1 over square root 2. And so this is a minimal torus. And then you can perform exactly the same construction, but having not only performing the connected set not only at 2 points, but at a very large number of points, then you can achieve new minimal surfaces. But also what you can do is that you can double the Clifford torus at fewer points, and then you would obtain constant mean curvature surfaces, and this has been obtained by myself and Adrian Butcher a few years ago. Okay, so the last remark I wanted to say is that this extends to higher dimension. Okay, so instead of taking the product of 2S1 here, what you take is you take a product of a sphere of dimension K1 and a sphere of dimension K2 that sits into a sphere of dimension K1 plus K2 plus 1. And then you can perform exactly the same analysis. You see that you have a bifurcation phenomena, and a lot of things remain true. Okay, so now the main question is, what remains in a general Riemannian manifold? So what I claim is that basically the three descriptions I have outlined, they still hold in a general Riemannian manifold. So let me be more specific. So first of all, about the existence of these concentric spheres, there is a theorem by Rouganier in the early 90s that says the following: if P is a non-degenerate critical point of the scalar curvature function, then a neighborhood of P can be foliated by constant mean curvature spheres. Then a neighborhood of P can be foliated by constant mean curvature small spheres. So exactly in the same way you would do it in Euclid, in the flat 3 torus. So you have a point, and then what you have is that you have constant mean curvature topological spheres, which are in fact extremely close to geodesic spheres, and they have mean curvature, and they foliate a neighborhood of this point P. What is quite surprising is that there is almost a converse to this theorem, but before saying this, I would like to say that there is a work by Stefano Narduli and Olivier Druet also that connect these solutions to the solutions of the isoperimetric problem. With a small volume constraint. So it should be clear that if you solve the isoperimetric problem with small volume constraint, then you basically what you expect is to have a constant mean curvature surface with very high value of the mean curvature, and you also expect that this surface is close to a round sphere. This is not so hard to see, but what is very interesting is that in fact Olivier Druet proved that the solution of the isoperimetric problem for small volume constraint is a sphere that concentrates at a point which is a maximal value of the scalar curvature. And then Stefano Narduli was able to prove that, in fact, this surface was one of the surfaces which was constructed by Rungangier, so belonged to these foliations here, one of these foliations when P is the point where the scalar curvature is maximal. But this requires quite some work. And very recently, Harold Rosenberg and Graham Smith, they developed a degree theory for convex constant mean curvature surfaces, spheres, with a high mean curvature, with large mean curvature. So there is by now a quite general existence result for constant mean curvature sphere with large mean curvature in any reasonable Riemannian manifold. Okay, so here in this result there are some constraints about the manifold. So it is not completely general, but basically it uses this result by Rungangier to get information about the number of constant mean curvature convex sphere you can find in a given Riemannian manifold. Okay. Now also this constraint about P being a non-degenerate critical point of the scalar curvature, where this non-degeneracy assumption can be removed, and I did it with Xinguang Zhu a few years ago. But what happened is that if you remove this information here, you get fewer information about the constant mean curvature sphere you construct. So I'm not so sure that this is really a very important result. What is more interesting is the recent result by Paul Laurin, and he proves a partial converse to this theorem. He says that if you have sigma h, a sequence of constant mean curvature spheres which are embedded, and you assume that the diameter of this sphere tends to 0 as h tends to infinity, and also you assume that the volume or the area of this sphere is bounded by a constant divided by h squared, still as h tends to plus infinity. So there are these two assumptions here, but so this is a quite natural assumption. For example, if you have one small geodesic sphere, then these two assumptions are fulfilled. Or if you have two connected sum of two small geodesic spheres, also this is fulfilled. But and the conclusion is that then up to a subsequence, sigma h converges to a critical point of the scalar curvature function. So you see, this is a very strong partial result of Rugangier's result, in fact, existence result. And this proves that if you look for constant mean curvature surfaces, somehow with mean curvature very large and with diameter is small, in some sense you should not expect to find them away from the critical points of the scalar curvature function. Okay, so the scalar curvature function plays a very important role in the existence of these spheres, constant mean curvature spheres in a Riemannian manifold. So unfortunately, in a generic Riemannian manifold, the story is slightly more complicated than this, and so there is a theorem of mine and Malchiodi which generalized this result by Rungangier in a quite a weird way. So the theorem says the following. So you assume that P is a critical point point of the scalar curvature function, and also you assume that the Hessian of the scalar curvature function at P is invertible. And to simplify the statement, what I will do is that I will assume that we consider that this Hessian that as a symmetric matrix, and that the Hessian has as an eigenvalue which is simple. So there exists an eigenvalue which is simple. So this is just to simplify the statement. Then let me call it lambda. And then there exist constant mean curvature surfaces obtained as a connected sum of two spheres, geodesic spheres of radius epsilon, in the following way. So let me do a picture instead of a longer. So what you do is that you have the point P, you have the vector, the eigenvector associated to the eigenvalue lambda here. So this defines a geodesic passing through P and having this vector as speed at the point P. And then what you do is that you go at distance epsilon here, and you go at distance epsilon here. So this is supposed to be epsilon. And then you draw two spheres. Whoops. This is not a very good sphere. But, the spheres are not very, well, you're in a Riemannian manifold. They are not supposed to be very round, but this is a bit too, a bit too far from reality. And then what you try to do is that you try to perform a connected sum here. And what happens is that the two cases might happen. So one of the case you obtain is something like this. And the other case you obtain is an embedded example. And whether you obtain one of the example or the other depends on the sign of lambda. So the second example you can obtain is like this. Whoops. So this one you obtain it when lambda is negative, and this one you obtain it when lambda is positive. So here, so this is extremely close to being two spheres of radius epsilon connected by a small neck. So you see that the zoology of constant mean curvature spheres in a Riemannian manifold can be more complicated than it was in flat torus or in a sphere. So for example, in Euclidean space, this would certainly violate the Alexander theorem that says that an embedded constant mean curvature sphere has to be a round sphere. But such a thing are possible in Riemannian manifolds if you have some mild hypothesis. So basically that this is fulfilled. So more complicated construction can be obtained in the same way. Now the second construction I wanted to outline is a construction which generalizes these constant mean curvature tubes. So here there is a theorem by. So what is a tube? So you give yourself a curve gamma, which is a closed curve, and you define the tube around gamma of size epsilon to be the set of points Q whose distance to gamma is equal to epsilon. So this is the geodesic tube around gamma. And so the result is the following. The result says, so there is a theorem by Mazzeo and myself in this case. So in higher dimension we needed a third person because we were not smart enough to do it in higher dimension, but in dimension 3 we could do it. And so the theorem says that there exists, let me state it, there exists a sequence epsilon I tending to 0 such that the tube around gamma of size epsilon I can be perturbed into a constant mean curvature surface with mean curvature equal 1 over epsilon I, and this is true provided gamma is a non-degenerate geodesic. So what is very important here is that the construction is possible only if gamma is a non-degenerate geodesic. And so far there is no proof that the condition which is known to be sufficient, there is no known result that say that this condition is also necessary. So this is an open problem to prove that being a geodesic is necessary. Which means it's necessary to have constant mean curvature tubes around the curve with mean curvature tending to infinity. So I have no idea how to prove this result. What is very striking in this result, I have no time to explain this, but what is very striking in this result is that the construction does not hold for any value of epsilon tending to 0. And this is in contrast with the result of Rungangier, which allows you to have constant mean curvature sphere with mean curvature being equal to 2 over epsilon for any value of epsilon small enough. But here in this case, because of the bifurcation analysis I told you about in the Euclidean case and in the sphere case, there is a resonance phenomena that prevents us from deriving the existence of these constant mean curvature tubes for any value of epsilon. So this is related to this bifurcation phenomena I have talked about at the beginning. Now, in the few minutes that remain, also, I would like to say that if you try the proof of this result here, so in the construction, you see immediately why you have to choose gamma for being a geodesic. And so at the beginning, it is not very clear, but even if you do formal computation, you find out that being a geodesic is the right thing to do, and for this it works. And if you try the same method and prove without this assumption here, then the method fails. So I strongly believe that being a geodesic should be necessary. Now, the last result I wanted to mention is a very recent result about the doubling of minimal surfaces. So here the idea is the following. So you start with a minimal surface which is minimal, which is oriented, and what you do is that you assume that it is non-degenerate. So in particular, what it means is that if you apply the implicit function theorem, you can find surfaces which are close to sigma. So let me christen this one sigma naught. So sigma naught will be here. And what you can do is that you can find surfaces which are close to sigma whose mean curvature is close to 0. So you can find a surface here, sigma epsilon, whose mean curvature is equal to epsilon, and epsilon is small. But similarly, you can find another surface here whose mean curvature sigma is minus epsilon, whose mean curvature is minus epsilon. But if you orient everybody in this way, here, what you have is that, so this surface here has mean curvature epsilon with this orientation, and this one mean curvature minus epsilon with this orientation. But if you switch the orientation here, then it turns out that they will have the same mean curvature, and what you can try to do is perform a connected sum between this surface here and this surface there. Okay? So this is what I call doubling of minimal surface. So the problem is to perform a connected sum between sigma minus epsilon and sigma epsilon to produce a constant mean curvature surface. So we need some assumption to do this. And the result is again quite different from the Euclidean result or the result you would have in the sphere. So the theorem, and I will end with this one by myself and son, is, so I already said that this has to be non-degenerate. Then I can cook up, what I can do is that I can cook up, I have the Jacobi operator about sigma. And I can cook up the function phi, which solves this equation here. So the Jacobi operator applied to phi is equal to 1. So if phi has a non-degenerate critical point, let's say P, and if phi of P is non-zero, then the connected sum can be performed at P. And so let me do one drawing. And so on one drawing, this will be very clear. So here I have sigma 0. So this will be sigma epsilon, and let's say that this will be sigma minus epsilon. And if epsilon is very small, in fact, you can see that the picture is exactly like this. So the graph, the function you get for the graph of sigma epsilon, if you switch the sign, it has almost mean curvature equal to minus epsilon. And so the idea is that you can only perform the connected sum when this function has critical points. So for example, the points where it is closer, so here, or even if we had a maximum here, we would be able to perform a connected sum here. Moreover, if phi does not change sign, then the surface you obtain are embedded. So if phi does not change sign, then the surfaces obtained are embedded. And for example, this is true when the minimal surface you start with is stable. Right. So this is where these are the results I have described here are all the results that hold basically for, you see that you always have non-degeneracy assumption to fulfill. So they will work they can be applied in a generic way, but they might not be applied in a specific situation. There is still many work to do because these are always sufficient conditions for the existence of constant mean curvature surface, but there is very little work about the fact that these conditions if these conditions are necessary or not. This is not well known. Okay, thank you for your attention. Finish here.